Hello, this is Gary LaRue, Technical Editor at Microwave Journal. It's my pleasure to welcome you to today's webinar outlining the benefits of modular real-time spectrum and signal analysis. It's presented by Ross Smith, Wade Loudermilk, and Michael Spinelli of RADX Technologies. Before we begin the presentation, let me cover a few points about our agenda. First, the webinar will last an hour. After the presentation, we'll have time for questions. And you may submit a question at any time during the hour. All you have to do is type it in the Q&A box on the right-hand side of the WebEx screen. Please make sure the setting shows all panelists. After the webinar, you will receive a copy of the presentation, and we're also recording it so you can watch it again and recommend it to colleagues who aren't able to watch it today. Now let me introduce our presenters. Ross Smith is co-founder and CEO of RADX Technologies. He's a seasoned executive with 30 years of taking tech startups from concept to liquidity and also turning around businesses. Ross has a bachelor's in electrical engineering from the University of Texas at Austin. He says it was granted a long, long time ago. He also claims to be an occasional angler. Wade Loudermilk is the other co-founder of RADX Technologies, and he serves as Chief Technical Officer. Wade is recognized for his expertise in digital signal processing, software-defined radio, cognitive radio, and software-defined synthetic instrumentation. Wade has a bachelor's in EE from UT Austin and a master's in electrical engineering from San Diego State University. Michael Spinelli is an applications engineer at RADX and is a certified LabVIEW developer with expertise operating and programming RADX LibertyGT instruments in LabVIEW, TestStand, and Python. Michael has a bachelor's in electrical engineering and is working on his master's from San Diego State University, where he's focusing on advanced digital signal processing as applied to wireless channel emulation. Ross, I'll now turn the screen over to you.
Thanks, Gary. Well, good morning to everyone, and thank you so much for joining us. This morning we're going to talk a bit about the benefits of modular real-time signal analysis. And in particular, we'll be talking about some of the RADX products we have to address that, in particular the LibertyGT1410, which is our advanced RTSA, and how its modular capabilities can be a benefit to customers both large and small. And by the way, if you're attending NI Week this year or IMS in Hawaii in June, stop by and see us. We'll be there, and you can see a live demo. So a little bit about RADX before I kind of launch into the heart of the subject. We're a small business established in 2011. We were founded primarily to focus on this. Wow, Siri just took over my world. Anyway, so a small business focused on test and measurement solutions and software-defined communications. And one thing that we've done that's quite important is we've established an exclusive license agreement with BAE Systems, where we have taken the technology used on the F-16 IAIS ATS program, and that's become part of the key technology inside our synthetic instrument technology. We're also a National Instruments Silver Alliance partner. And what you'll see today is a discussion about our LibertyGT family of integrated modular RF and microwave T&M solutions, and in particular the 1410 model, which is our wideband 26.5 GHz RTSA. The LibertyGT products are a modular solution based on NI technology and our software, and we were the recipient of the 2014 Frost & Sullivan Best Practices Award for Innovation in Test and Measurement. So why RTSA? The main reason is that it's really designed to solve a specific problem, which is looking for elusive signals. If one looks at a real-time or a non-real-time spectrum analyzer, a conventional spectrum analyzer, you'd find that it's not well suited for reliably detecting, capturing, and analyzing elusive signals that are low probability of intercept, things that are intermittent, spectrally diverse, or frequency agile. And those types of signals are quite pervasive today. But the tools that most engineers have at their disposal are kind of analogous to this picture here, where you have in an old-time camera, and you're trying to capture a very rapid event, and it's just not well set up to do that. And the reason for that is that if you look at a spectrum analyzer and it's trying to capture a rapid event, you won't see it. And here's a good example. This is a conventional spectrum analyzer, and you see the noise floor down here, but what you don't see is this missing 320 nanosecond pulse. And that's primarily because a conventional spectrum analyzer has this non-real-time capture, store, and process paradigm where it captures data, it processes it, captures it, processes it, and in between those periods, there's a data gap where you may miss signals. And those missed signals are the things typically that you would want to capture if you're looking for intermittent events. So to address that, folks, before our time, came up with the notion of a real-time or gapless processing approach to doing real-time spectrum analysis. And here, because of the methodology that's employed, you can actually, capture these types of fleeting signals. So the same 320 nanosecond pulse that we were looking for previously that we could not see now shows up quite readily on the RTSA. And you can see it here in the histogram, spectrogram, the trigger, as well as the real-time spectrum displays itself. And that's because the RTSA employs gapless processing. So unlike a conventional spectrum analyzer, a real-time spectrum analyzer captures and processes in parallel, so there are no missed data samples. We typically do that, at least in our case, with a dedicated FPGA engine that uses a high degree of overlap with high-performance FFTs. And that does require, more firmware and software, but that's how you get the performance that we're able to achieve. The net result of that is deterministic and very fast response. It gives you good real-time performance. And an expression of that is this figure of minimum duration signal, 100% probability of intercept with full amplitude accuracy. I realize that's a mouthful, but that's an important metric because it tells you what is the shortest signal that I can reliably detect and analyze in an RTSA. And we'll talk about that a bit more. So because of the market, and the market has grown substantially for RTSAs as well as for the need for high-performance RTSAs, the big guys in the marketplace, Keysight, Rohde Schwartz, and Tektronix, have all brought out very impressive instruments that do wideband RTSA functions. And if you look at the common characteristics between them, they're typically 500 megahertz or more, really good RF characteristics. They have, kind of all the advanced RTSA features, especially advanced triggering. And they're able to achieve a 100% POI number between 700 nanoseconds to about 3.2 microseconds, which is quite remarkable. They also provide other kind of VSA functionality, so vector signal analysis, spectrum analysis, and proprietary measurement suites for kind of post-processing. You can add RAID to these things, usually externally, so you can record a long period of spectrum to look at for specific signals or do after-action analysis. And they range in price from about $170,000 to $250,000, depending on options. In May of last year, we introduced the first modular RTSA, which we call the LibertyGT1410. And because of our dedication of an FPGA module to doing real-time functions, in particular FFTs, we were able to set a new record for RTSA performance. The LibertyGT1410 is the highest performance wideband commercial off-the-shelf 26.5 gigahertz RTSA available today. We can process up to 62.5 million FFTs per second. And that indirectly translates to our ability to deliver 100% POI of 320 nanoseconds. And that's with full amplitude accuracy. And that term of full amplitude accuracy is important because you want to make sure you're comparing apples to apples when you look at these different systems. We also support 765 megahertz of real-time bandwidth, also with full amplitude accuracy. We priced this system very competitively at about $150,000 US, and that gets you a turnkey system with all the bells and whistles that you need to do advanced RTSA, vector signal analysis, spectrum analysis, bit error rate testing, a wide suite of demodulations, et cetera, et cetera. And that's important. The pricing is important, because it's good for our customers, but also we're able to address what people have called a modularity price premium, and we'll talk about that more downstream. And this system is the only modular system available today, and there's some real benefits that come from that. So before we talk about modularity, it's probably good to see how this stacks up against the other guys in the marketplace. So in terms of FFTs per second, we really have the highest performance in the industry. We can support up to about 62.5 million FFTs per second, and that compares quite favorably to the other guys. They're typically, about, well, they're a fraction of what we can do. And in part, that's just architecturally, and because that's been our focus is real time. In terms of 100% POI, we're also the industry leader at 320 nanoseconds. That compares to about 3.5 microseconds for the Keysight N9040B, about 910 nanoseconds from the Rohde-Schwarz FSW26, and about 700 nanoseconds for the Tektronix RSA 7100. And this metric, of course, lower is better, and so this is indicative of the fact that we maintain that we have the highest performance system of its kind in the industry. In terms of real-time bandwidth, the 1410 achieves 765 megahertz, and that's across the 26.5 gigahertz range. The Tektronix actually ekes out a little bit higher bandwidth at 800 megahertz. We're kind of in spitting distance of that, so to speak. The Keysight and Rohde-Schwarz products have about 500 megahertz, give or take a little bit, of bandwidth. So we're higher than those by about 50%. Keysight also has a nice modular solution, but it does not support RTSA, and it only has 160 megahertz of bandwidth. I put it there for completeness. Displayed average noise level is a good indication of receiver, RF capabilities, and all of these products, have really good DA&L performance. If you look at it at 1 gigahertz, we're at about minus 166 dBm per hertz. Keysight, has a slight advantage there at about minus 171. And we're, in the same ballpark as Tektronix, a little bit better than Rohde-Schwarz in this case. And we really can't claim victory for this, except for the fact that we're partnered with National Instruments, and it's the NI 5668 VSA that really helps us achieve this really good RF number. And so that's kind of part of the advantage of modular instruments, so we can leverage really good technology from our partners, and in this case from National Instruments, helps us achieve this really good RF capability. And finally, on price. So as I mentioned, the 1410, configured fully, is about $150,000, and that compares, against, the competition of the Keysight at about $210, Rohde-Schwarz at about $170, same for Tektronix. So we have a slight price advantage against the competition as well, and that also comes from our business model, which is really, we'll talk more about this, but we're also really focused on software, and so we're using commercial off-the-shelf hardware, and there's some pricing advantages that accrue to our customers as a result of that. So in summary, if you look at price, minimum signal duration, 100% POI, real-time bandwidth, FFTs per second, noise figure, I think we arguably have kind of the best set of specs in the industry for this kind of product, wideband 26.5 gigahertz RTSA, and it is the only tightly integrated modular system of its kind. And I think that's really important, especially if you're focused on not just the acquisition price and solving a near-term problem, but looking at the life cycle cost of the system. And that's really important to program managers and to people in finance, because you may keep this instrument for a long time. What is the overall cost that your organization is going to incur associated with that piece of equipment, over its life cycle? And that's where modular really has a great benefit. So let's peer into a modular system, in particular the 1410, to understand how it's comprised, and that will give you some good indications as to how these benefits accrue. So inside an RTSA, ours in particular, the modular LibertyGT1410, you'd find an enclosure, and we have our own touchscreen enclosures that are patent pending, and that gives you kind of the look and feel of a conventional boxed instrument with the all the modular goodies inside, and it's really good for serviceability and maintainability because you can open it and swap modules out and things like that. You can also use a conventional National Instruments chassis. For the 1410 capability, we require 24 gigabyte per second backplane, which gives us the ability to stream, hundreds of megahertz of bandwidth, all around the backplane. We also have a collection of NI modules inside the system. In particular, for the 1410, we have the 8880 embedded controller, which is a Xeon-based controller that we populate with 24 gigs of memory and a big solid-state drive. We have the 7976, and that should be PXI E7976, and that's the FPGA module. And then we have the PXI E5668 VSA, which is the RF component that really brings the system to life. In all of our systems, we configure it to meet specific requirements. So one of the joys of a modular system is that if you have a specific requirement where you need a DSO added or some other feature added to our system, we can readily do that. We also add signal conditioning in many cases, depending on what your requirements are, and that can vary from switching, filtering, amplification, and attenuation. We have our own modules that we developed, and also we use things from NI and other COT suppliers as well. And then lots of options, whether it's RAID options. We use RAID modules from Conduit or 10 gig Ethernet from SPD, displays, solid-state drives, etc. So COTS accessories that round out the system. So you combine that hardware with our real-time software, and that's really the heart of our system. We call it our real-time measurement science firmware and software, and we have a configuration that's specific to the 1410 RTSA. What's interesting about this is it's really been a labor of love. We've spent about, between us and BAE Systems, about 100 man-years of effort building this real-time software. And unlike a lot of modular approaches, which are kind of a do-it-yourself thing, we have developed a tightly integrated set of applications that all work together very well. You can see here on this screen, which is the home screen, and you'll see that in the demo, there are a bunch of apps here, and they all work together as a system. We manage the concurrency, that they can share data, and so it's a really interesting approach to modularity because it's an integrated package. And it has a complete set of applications that are required to really do your job, SpecAN, RTVSA, RTVSG, et cetera, and they all interact very well together. So you don't have to go do this yourself. We've done it for you. We also have really good support for third-party tools. And one thing that you see here, and Michael will talk about this a bit in the demo, is the fact that there's concurrency support. So the little green arrow there means that each of these applications is running concurrently, which is one of our clear advantages. So a base system with all those components of hardware and software, it looks like this, either what we call the R version, which is a reference platform using a standard chassis of about 148.5, or a benchtop version with our touchscreen enclosure is about 168.5, and you can order that as a turnkey system, or you can also buy it in parts. We'll talk about that in a moment. I mentioned that the pricing of our system is interesting because we use COTS technology underneath. So this actually exposes how we get to that price point. If you look inside our system, you'll find that, here's a quotation for the NI gear that goes in it, the modules, et cetera. That adds up to about $110,500. And then the RADX software and services to integrate this and test it is about $38,000, which gets you to $148,500 MSRP. What's interesting about this is that you can buy these modules from us as a turnkey system, or you can buy them from NI directly, and that's really unique in the industry. If you're a big company or an educational organization, or depending on who you are, you may have a great discount from NI, and you can take advantage of that because you might be able to buy it for a better price than we can, and you can consign those modules to us, or we'll come to you and integrate them for you. So there's a lot of flexibility here that gives you, our customers, a really good range of how you actually buy a system, and you can save a lot of money by doing that. So now let's get into the benefits proper. If you look at modularity from a high level, really, modularity is not an end, it's a means, and the means to reduce swap, size, weight, and power, and total cost of ownership. And the savings that you can achieve from that can be significant based on what your application is and the life cycle. We reduce swap, size, weight, and power for multiple instrument applications because we can support multiple functions in one box. And we use this technique of software-defined synthetic instrumentation to use the same modules for multiple functions, and that further reduces the swap and lowers costs. We also have a built-in high-performance test executive PC that's the embedded controller for the system, and that saves you from having to buy one of those too. We reduce total cost of ownership by letting you basically perform logistics at the module level. So spares, repairs, calibration, and tech insertion, you do at the module level, not the system level, and that has a lot of big cost implications. We also have gone to great lengths to enhance programmability, test program maintenance, and third-party application support that also has a big impact on lifecycle costs. And then lastly, we improve throughput through application concurrency. As I showed you previously, you can run multiple applications at once. That means that you can get more units through test than you could ordinarily. Things that we've tried to address fundamentally are the modularity price premium, so that a single box RADX system can compare favorably to a single box competitive box instrument, which is quite unique in the modular business. And also, I mentioned the fact that we're tightly integrated as opposed to do-it-yourself. So from that perspective, there's a whole hit list of things that we like to do to make sure our systems, achieve all the benefits of modularity. I won't bore you with the details on that, but you guys will have the presentation after the fact. I'll just kind of explain these as we go through them. So I mentioned multifunction, reduces, swap, and TCO, and this picture kind of illustrates that, where we have these different apps that run on our system that replicate the functionality of discrete instruments. So one LibertyGT1410 can replace multiple box instruments to reduce TCO and swap, and also improve mean time to repair. And plus, because of the concurrency capability, we're able to improve throughput. Module-level support and tech insertion is a really important capability because that lets you spare, repair, do cal, and tech insertion at the module level. So here's the inside of one of our enclosures, and you can see the modules that go into that. If one of those modules fails, you simply send that module back. You don't send the whole system back. So that has a big impact on a number of factors as to how you run your business. The other thing that we have are open slots here that lets you add capabilities either at the time of acquisition or downstream. So if, for example, you want to add RAID capabilities, you can do that inside the box. There are 9 open slots there, so you can have 64 terabytes of RAID inside this box if you want to do long-term spectrum recording at very high bandwidths. And it's also true for other instruments. You can add a DSO, other capabilities, because it's an open system and it's designed for upgrades. We have lots of options for the system, so it lets you tailor the system to meet your requirements, whether it's additional modules with specific capabilities or software or the combination of the two. As I mentioned, we've done a lot of work to optimize our solution to be a solution, not a collection of parts. And so, a lot of modular systems are kind of like IKEA projects where you get a manual and a screwdriver and you go to town for a while. We've really taken the tack of integrating a turnkey solution so that you can spend your time programming your application, for automation, and not trying to basically synthesize a complete instrument package. That makes a big difference in your time to market and your cost. So if you look at our measurement science firmware and software, it's over a dozen apps and meters, has a very intuitive touchscreen user interface. You can program it to your heart's content for automation, and that approach really simplifies your life because you get a good out-of-the-box experience, and you can focus on programming things specific to your application. We've also spent a lot of time making it easy to program. We have an API that enables you to program the system in LabVIEW, TestStand, Python, C, C++, or Java. And that API talks to all of our apps and all of the functions within the apps. And that lets you basically spend your time, creating something that's specific to your application as opposed to worrying about the fundamentals of the application, the fundamentals of the instrument itself. Now, we also have a built-in test executive, as I mentioned, that lets you run all these programs here, which saves you from having to have a discrete test executive. And if you look at it kind of overall, we use this one system with its one programming environment to replace the complete collection of systems, discrete systems. So in effect, this really is an automated test system on your benchtop. Inside baseball aspect of the system is it's a modular software-defined synthetic instrument with a hardware abstraction layer. And that's important for lifecycle costs because we have this HAL and a concurrency manager that isolates the hardware down here from the applications and also isolates the hardware from your application as well. So if one of these modules goes end of life, which they all do, and you have to replace it, because of our hardware abstraction layer, if you use one of our qualified replacement modules, so let's say the VSA goes end of life, we provide another VSA that's also a module that plugs into the system, then in effect, you don't have to change your test program at all. And we actually, at IMS, will be demonstrating that in 15 minutes or less. And that's a really powerful feature because no longer do you have to spend a lot of time and money to change your test program to match things that go end of life. It also lets you avoid having to buy end-of-life components. So, you get an end-of-life notice, then you have to do a lifetime buy and buy a bunch of the same old products. Don't do that. You can simply buy the new product that will replace the old one, and it will not affect your software. And this has a huge impact on lifecycle cost. We're also app-friendly. There are a lot of third-party apps and NI apps that are available through the National Instruments Tools Network ecosystem. Here I show about 38 that are relevant to the RF test and measurement that we do. And we've used several of these on different projects, and it's a huge benefit to a user simply because you don't have to reinvent the wheel. If you need GPS, you can use the NI GPS toolkit. If you need SARSAT, you can use the Olympic Engineering SARSAT. So these are great ways to extend your capabilities without having to expend a lot of engineering resources to do so. And that's very unique in the test and measurement world as well. It's much more of a PC model than a conventional test and measurement model, and we embrace that. We're cost and low risk. As I mentioned, we're using NI, PXI, and other key companies' PXI technology inside the box, like conduit RAID modules and things like that. And that really mitigates the risk of our own hardware development. I mean, we're pretty good at that as well, but we're standing on the shoulders of giants that do this for their main job, and that really makes the system low risk. We've also incorporated this key technology from BAE Systems, which is the software-defined synthetic instrument technology they have on the F-16 program. And something that's also unique about our approach to business is that we have a lot of big customers that want to make sure that they can support these programs or these instruments over time. So we make our source code available. It's either an escrow or as a source code license, and that gives you security that you'll be able to support this even if we disappear. And that's a standard thing that we do. And lastly, we have a flexible business model. You can choose how you buy a LibertyGT system. You can buy a turnkey product from us where you place a purchase order and we ship you a box with all the goodies in it. Or you can buy a kit. And a kit would mean that you buy the NI modules from NI, or maybe you already have them and you just want to buy software and or an enclosure for it. So this flexibility means you can really tune this to your budget and to your company's abilities. So if you have the ability to integrate a system yourself and you have a good buying organization that can get a good deal on these modules, save that money. We're happy to help with that. So if you look back on the benefits that derive from being modular, there's a whole list of them, from multifunctionality, software-defined synthetic architecture, et cetera, and to achieve these benefits, you have to be a modular instrument, and we're the only guy in town that has that for a wideband 26.5 GHz RTSA. So in summary, we're the highest performance wideband COTS instrument available today. We're competitively priced, and we have the only integrated solution on the marketplace today. And so I think that if you're interested in a wideband RTSA, it's worth looking at this, not only because we have great performance and a good price, but also because of the long-term benefits that derive to your organization because of modularity. There's more stuff online, videos and brochures, and as I mentioned, we'll be at some events, NI Week and IMS, so be sure and come by and see us or drop us an email, and we're happy to work with you quite a bit more. So now let's segue to demos. I'll be handing this off to Michael here shortly, but I'll just try and set up the demos very quickly. We have two demos we're going to show today. One is, and there's a typo here, this should be 324 nanoseconds. We have a 324 nanosecond frequency hopping pulse demo where we're going to generate a pulse signal on our vector signal generator inside the system. And we'll send that both to a conventional Spec and to the RTSA and look at the results of that. We'll capture that data, and then we'll do some third-party analysis on it. And we'll do the same thing, more or less, with just looking at some spectrum. We'll look at 802.11. I think we're looking at 802.11b today in the 2.4 gigahertz range. And we'll just capture that from an antenna. We'll look at it both with the RTSA and the conventional Spec-N. We'll grab that data, store it on disk, and then we'll use some third-party analysis to look at that after the fact. And it's kind of typically how you would use an RTSA. And with that, I'll hand it over to Michael.
Hello, my name is Michael Spinelli. I'm an applications engineer at RADX, and I'll be doing the demo today. The screen we're currently looking at is the home screen. And the home screen provides access to several important applications on the LibertyGT. Each application has an associated icon. And if we look at some of these, starting from the top left, we have a spectrum analyzer, a real-time vector signal analyzer, a real-time vector signal generator, an audio analyzer, a bit error rate tester, a digital storage oscilloscope, a multi-channel real-time vector signal analyzer, a multi-channel real-time vector signal generator, a digital multimeter, real-time spectrum analyzer, both non-export controlled and export controlled. We have a station, calibration, and alignment, a full performance verification test application. Control and test examples contains RADX provided examples of programmatically interacting with the LibertyGT. Third-party and auxiliary apps is where you can put non-RADX developed applications and software. And then one thing you may notice is the RTVSG icon looks different than the other icons. The first thing is the green arrow in the bottom right. And as Ross mentioned, that means that application is running. And the LibertyGT can actually support running multiple applications at the same time. Each application that is running will have the same green arrow. The other symbol to note is in the top left, the transmission symbol. It means the RTVSG is actively transmitting a signal. And every application that is actively transmitting a signal will have this same symbol. So the signal that the RTVSG is generating is a frequency hopping pulse. The pulse width is 324 nanoseconds. The pulse repetition interval is 40 milliseconds. And the composite signal is centered at 5 gigahertz. So let's go open the RTVSG and just get a feel for this application. One thing to note is the transmission symbol in the top left of the navigation bar. That symbol will appear for every single navigation bar. That way you know that even though you're not looking at the signal generator, you know a signal is being generated. The controls, if we go on the right-hand side of the screen, we have an application bar where we can pause generation, go to a default state, turn the RF off and on, turn modulation off and on, or save and load a predefined configuration. We can configure what type of waveform we want to generate, such as analog modulated waveforms, digitally modulated waveforms, arbitrary waveforms, sweep waveforms, or pulse modulated waveforms. For LibertyGT configurations that support multiple RF outputs, we can select which RF output port on which we want to transmit our signal. Sweep, I can control what I want to sweep, either nothing, off, or frequency, level, or frequency and level. Sweep repeat, I can sweep once, or I can continuously sweep. Sweep type, step is where I set predefined start and stop points, and it'll sweep in between those. We have selected list, which is where we define every single sweep point, and it starts from the top of the list and goes to the bottom. And we can see our list down here in the bottom. We can scroll up, scroll down. Each point has a frequency, level, and dwell time. We can add points. We can select a point and remove it, or modify the point. We can save this to a file. We could load a predefined list, which is actually what I use to load all these points into the RTVSG, or we can delete the list and start over. Now let's analyze this signal on first a conventional spectrum analyzer. Then afterwards, we'll analyze that same signal on the RADX real-time spectrum analyzer. So I'm going to go to the home screen and open up a conventional spectrum analyzer. And it's going to open up here. So I'm going to take this to full screen. And I'm going to load the configuration for this conventional spectrum analyzer from a file. And so the conventional spectrum analyzer is now configured to analyze the frequency range of which our frequency hopping pulse is being generated in. And if we look, we pretty much, all we see here is a noise floor. We would expect to see the spectrum of our pulse move between several frequencies. but we don't see that. We don't see the signal. And this is because of the gap processing of the conventional spectrum analyzer, where we're missing the data because of the gaps. So now let's go look at the RADX real-time spectrum analyzer so we can do a comparison between conventional spectrum analysis and real-time spectrum analysis. So we're going to close out of this conventional spectrum analyzer. We're going to open up the RADX real-time spectrum analyzer. You notice the green arrow in the bottom right means the real-time spectrum analyzer is running. And then also quickly notice in the top, we see that transmission icon because the RTVSG is transmitting. And the first thing, before we configure the RTSA, let's first go over the user interface. On the left side of the screen, we have our plots and indicators. The top left plot is our histogram. Below that is our spectrogram. We have a real-time spectrum to the right of the spectrogram. In the top right, we have our trigger plots, which show time domain data, both I and Q, for captured data signals. And in the top, we have our important parameters and settings. On the right, we have our controls. The application control bar is in the top, and then below are access to our individual control menus. So now let's configure our RTSA to analyze the frequency hopping signal we're generating. So we're going to go to frequency. We're going to set the center frequency to 5 gigahertz. And we're going to set the span to 320 megahertz. We're going to go back to the main menu. And already from looking at the histogram and the spectrogram, we can see there's several pulses, and we already see a lot more information than we did with the conventional spectrum analyzer. However, the histogram, the pulse spectrums, they're hard to see. They're dark blue, and that black background is not enough contrast. So let's configure the histogram to make our frequency hopping signal more easier to view. So we're going to go to the real-time spectrum menu. Emphasis, we're going to increase this to 90%. And if we look back in the histogram, we can see our pulse spectrum. Now they're brighter blue, so it's much easier to see. However, those pulses, they fade away too quickly. Let's slow that down, have them stay on the screen longer. To do this, we're going to go to persistence time. We're going to increase this to 1 second. And if we notice, the pulses stay on the histogram much longer. And lastly, let's increase the color saturation to 70%. What we've done here is we configured the histogram to make it easier to view the particular signal that we're trying to analyze, which is our frequency hopping pulse. Let's go back to the main menu. Below the histogram is the spectrogram. And we can see all the pulses and the orange dots and lines. And the spectrogram shows spectral frames over time. Now, to understand what a spectral frame is, let's go up to the top of the screen and look at our important settings and parameters. In particular, number of FFTs per second. We're currently performing 533.333 thousand FFTs per second. And our sweep time, 30 milliseconds. And the sweep time controls how often our spectrogram and spectrum plots are going to update. So to create a spectral frame, we'll take all the FFTs that we have performed in this 30 millisecond period, and we'll combine them by taking the maximum values for each frequency bin. That spectral frame will then be added to the bottom of the spectrogram. The real-time spectrum takes the last FFT being performed every 30 milliseconds, which is why we might not see the pulse. However, we can go to the real-time spectrum, we can turn on a max hold, and we can see our pulses appear. So let's turn this back off. Next, let's capture the time domain data of just one of these pulses. To do this, we're going to use frequency mask triggering. So let's go to the trigger menu, trigger type. Now there's 3 types of triggering we can do: free run, frequency mask, or time domain. We're going to select frequency mask. We're going to load a predefined mask. So I'm going to go to load mask. I'm going to select my mask. And I created this mask using the real-time spectrum analyzer's built-in mask editor, and that's accessed by pressing Edit Mask. You can turn the mask on. If we go back, and let's look at the bottom right plot, and we can see our frequency mask in green. And then notice the vertical line. That's part of the mask on the right, the top right of the plot. And that's centered at the frequency of the pulse that we wish to capture. So when this pulse is generated, it'll enter the mask, which will create a trigger event. And we'll capture 1 millisecond our pre-trigger time before the trigger, and 1 millisecond after that event, our post-trigger time. The captured data will then be displayed in our trigger plots, both I and Q. We'll specify a file where we want to save this data, and we'll use the default, which is a waveform and a current timestamp. Let's arm our trigger. And when the pulse gets generated, it'll enter the mask, as we saw, and then our plot's updated. We can see our pulse. Let's save this data to file. And as Ross mentioned, you can use a variety of different analysis and measurement tools to perform post-processing. So let's do that. We're going to use a program that we created in LabVIEW to analyze this pulse. So let's go to the home screen. We're going to go to Control and Test Examples. We're going to open up our pulse analysis program. First thing we want to do is load our pulse that we captured. So let's select that file. We noticed 3 plots. Let's go over those real quickly. The top plot is the power burst time for our entire captured data sequence, the full 2 milliseconds. If you look in the middle, you see the yellow vertical line. That's actually our pulse. So what this program did is it scanned the captured data sequence. It found the pulse. It displayed the pulse's power burst time. That's the middle plot, and the pulse's spectrum. And then it also made 3 measurements. Pulse width, which we measured to be 324.051 nanoseconds, which makes sense considering we set our pulse to be 324 nanoseconds on our real-time vector signal generator. Pulse rise time, we measured that to be 22.605 nanoseconds. Pulse fall time, we measured that to be 22.16 nanoseconds. So what we've done here, we use the RADX real-time spectrum analyzer to detect and capture just 1 pulse of a frequency hopping signal and save it to file. We use the post-processing software, which again is a variety of different options. You could use LabVIEW, you could use MATLAB. We use LabVIEW in this case, and we perform several different measurements. The next example we're going to do is we're going to analyze the Wi-Fi environment. To do this, I'm going to connect a Wi-Fi antenna to the RF input port of LibertyGT and look at Wi-Fi at 2.4 gigahertz. So first, let's close out of this example. And we're going to temporarily close out of the real-time spectrum analyzer. And you'll notice the green arrow will disappear. We'll wait for this to close, and then afterwards, I'm going to close out of the real-time vector signal generator. As we have an antenna this time, we're not generating the signal. And then I'm going to open up a conventional spectrum analyzer. What we're going to do is we're going to look at that Wi-Fi signal in the conventional spectrum analyzer, and then on the RADX real-time spectrum analyzer. So third-party apps, open our conventional spectrum analyzer. And the conventional spectrum analyzer is going to load and initialize. Let's maximize this. And again, we're going to load our settings from a configuration file. Okay, so we're now centered at 2.45 gigahertz. We have a span of 100 megahertz. And what we see is, we see the noise floor, and we don't really see much of our signal. Sorry about that. And we see parts of the Wi-Fi signal appear. We can see here. We can't really tell which Wi-Fi channel that came from. We can't really see how that signal varies over time. And what if we want to capture just one Wi-Fi channel? And we can't really tell where it is or see enough of that signal to be able to do that. And this is again related to the gap processing of the conventional spectrum analyzer. So let's now open up the RADX real-time spectrum analyzer so we can then compare the conventional spectrum analysis to real-time spectrum analysis. So let's close out of the spectrum analyzer. And then we're going to open up the RADX real-time spectrum analyzer. You notice the green arrow. That's because this application is running. Let's configure this the same way we did with the conventional spectrum analyzer. So frequency, center frequency, we want 2.45 gigahertz. Span, 100 megahertz. go back to the main menu. And the reference level, we'll go to amplitude. We're going to lower this to, let's say, -20. And already from our plots, we can see a lot more information. We can see there's approximately 3 wideband Wi-Fi signals and several other signals being generated. And from the spectrogram, we can see how those signals change over time. Now, one thing that we couldn't do with the conventional spectrum analyzer was capture the rightmost wideband Wi-Fi signal. This happens to be a Wi-Fi channel centered at 2.642 gigahertz. And to do this, we're going to use, again, frequency mask triggering. So let's go to Trigger menu, Trigger type, Frequency mask. And let's configure our pre- and post-trigger time before we load our mask. Let's make our post-trigger time 50 milliseconds. And our pre-trigger time 50 milliseconds. So we're going to capture a total of 100 milliseconds, 50 milliseconds before a trigger, and 50 milliseconds after. Now let's load our mask. Going to go to Load Mask, Predefined Mask, turn it on. And again, this was created using the real-time spectrum analyzer's built-in mask editor. We see our mask appear in the bottom right, in the green. So when our signal is generated of the Wi-Fi channel that we're trying to capture at the 2.642 gigahertz, it'll enter this region, which will create a trigger event. It will capture 50 milliseconds before the trigger, which is again our pre-trigger, and 50 milliseconds after the trigger, which is our post-trigger. We want to save this to file, so let's specify a file name. We want waveform and timestamp. Let's arm the trigger. And we can see our Wi-Fi signal, part of it, displayed in the I and Q time domain plots, the trigger. We're going to save this data to file. And as Ross mentioned, you can really use a variety of commercial, off-the-shelf, commonly available measurement analysis tools. So we're actually going to use the National Instruments WLAN measurement suite to perform post-processing on this Wi-Fi data signal that we just captured. So let's go open our program that contains the NI WLAN measurement suite. And then go to the home screen. Control and test examples. Open up our program. Let's first load our file. Select the one we just captured. Let's press Start to perform analysis. And the first thing you're going to notice are these 2 plots. That's our time domain for the entire 100 milliseconds that we captured, both I and Q. Next to that, we have important parameters related to the capture, such as what center frequency we had, what was the span, the reference level, when, the time we captured it, how long, 100 milliseconds, and how many samples, 128,000. And then above that, the NI WLAN toolkit is very extensive, and you can perform a very thorough analysis. Several different options. So for example, right now we're set to analyze 802.11a and G, which is what that signal was. But we can go and select 802.11n and a variety of different other ones provided by this third-party analysis toolkit. And below that, we have our table of results. And these are all the measurements that we performed. And so what we've seen with these 2 demos is that we can use the RADX real-time spectrum analyzer to detect, capture, and do analysis on time-varying and spectrally adaptive signals, such as a frequency hopping pulse, and as a standard 802.11 Wi-Fi. So that concludes this demo. So I'm going to go ahead and pass this back to Ross.
Thanks, Michael.
So are we ready for questions?
I think we are.
Okay. Well, Ross and Michael, thank you both for a really informative presentation, and I love the demonstration. It really shows the capability of the instrument and the software. So we do have about 10 minutes for questions, so I'll encourage our audience, if you have any questions you'd like to ask, please do so. You can type them into the Q&A box on the right-hand side of your screen, and we will see if we can get to as many of those questions as we can in the next few minutes. So let me start with this one. I think you said the upper frequency limit is like 26.5 gigahertz, or what is the upper frequency limit, and can it be extended?
This is Ross. That's correct, Gary. The current system, the 1410, is limited to 26.5 gigahertz. We have a prototype of a 50 gigahertz version working in the lab, and that's something that we'll bring out probably later in the year. We have a number of customers that have asked for that. So because it's a COTS foundation using PXE, as different modules come out from different suppliers, we're able to incorporate those and extend the range.
Okay. You also, I noticed, and I think Michael referred to this in the demo, about export model and export restrictions. Can you talk a little bit more about that? What export license restrictions are on the system?
So the Department of State and Department of Commerce have defined some restrictions on RTSAs. What Michael was showing you today is actually export limited, even though the signals we were looking at wouldn't require it. If you're under 170 megahertz of real-time bandwidth and greater than 15 microseconds of 100% POI, then we can ship what we call RTSA 1, which is not export controlled. If you need to go into higher performance, like the thing we were showing today, which is a 320 nanosecond, 765 megahertz bandwidth, that is an export controlled item. That's actually 3D001 if people are familiar with ECCN numbers. And that's true for us. It's true for Keysight, Rode, Tektronix. We all have those same limitations. So you'd have to get an export license. It's not ITAR, and it's straightforward, but it is something that we have to go through a license process to export.
Okay. You have internal storage. How many minutes can you record with the internal RAID?
That's a little bit of a loaded question because it depends on what bandwidth you're recording and how many minutes you want. A good kind of rule of thumb is the conduit RAID modules we're using today are 8 terabytes per module, and that translates to about an hour of 500 megahertz. And so, it kind of depends on what you want to do. If you wanted to do, 5 hours worth at 500 megahertz, we would put 5 RAID modules in, or you would, and that would, that would accomplish that. There are 9 available slots inside the enclosure, so you can have up to really 72 terabytes of storage, and that would translate to basically 9 hours of 500 megahertz. And if your bandwidth requirements are less, you get more time. If they're higher, you get less time. So it's pretty flexible.
Yeah, it sounds like a good amount of time, certainly. So again,
it all depends. It all, on the customer's requirements.
Right. So again, to our viewers, if you have a question, feel free to submit it. We do have time for questions. Just use the Q&A panel on the right-hand side of your WebEx screen. Let's go to another question now. You talked a little bit about some of the software that can be used for analysis, and I recall you mentioning MATLAB. Can you use MATLAB to analyze the captured data from the system, and can it run on the system controller?
Yes, you can. We've actually used MATLAB, and it's very powerful and quite ubiquitous. So a lot of people like to use that. And we've done that, and there are a lot of MATLAB toolboxes that you can also use to analyze that, things after acquisition. I think we've used the signal processing toolbox. They also have a wireless LAN toolbox. And, the embedded controller is a Xeon 8-core processor with 24 gigs of memory, so it runs MATLAB very well.
Can you talk a little bit about some of the, maybe the applications that you're seeing being used for the equipment?
It's interesting that, the core purpose of this particular instrument is RTSA, but because it's really a general purpose instrument that's been tailored to that, we do see people adding other capabilities to it. So vector signal generation, as well as it's more traditional things like DSO or DMM. So one of the applications that we've seen is someone who's really focused on RTSA, but also wants to do an additional analysis, and so they've added some other instruments to it. The most of where we see at least applications in the U.S. tend to be in aerospace and defense applications, or people doing spectrum monitoring specifically. We have some overseas customers that are using it for more traditional kind of what we would consider to be FCC kind of spectrum monitoring here to look for interference and people that are violating their licenses. So if it's a licensed chunk of the spectrum and someone's using that inappropriately, you can use this to record that, and it provides a good historical file as to when they're infringing and when they're not.
So it's legally acceptable that you could show that somebody's violating the spectrum terms.
Oh yeah, I mean we especially because we capture so much spectrum, you can indicate, and we timestamp and do all the normal things that you would do for a spectrum monitor. So, and then you can geolocate that and say, well, you know what, on Tuesday you were transmitting it at 3 a.m. and you shouldn't be. So it's
right.
We don't do as much in the application spaces as our customers would do with that, but we provide the fundamentals to support that.
Okay, and you mentioned aerospace and defense. Signal intelligence, radar kind of radar signature type applications?
Our customers are so sensitive in that world. I would say that, it is those broad class of applications, a lot more probably in the signal intelligence world where, people want to look at a chunk of spectrum and see what's going on there. But, the customers are pretty, sensitive there, so enough said.
Yeah, don't say anything that you'd have to shoot us for. So how about field applications? How can this be configured to go out in the field?
It is. I mean, it's not mil-spec rugged. It is, the enclosure itself is designed. It's really designed for a benign environment where we do have people that deploy it, typically in a shock rack kind of mount, and that's useful for both kind of a vehicle mount as well as an aircraft. The power supply itself actually supports 400-volt operation, so it's well suited for that. But like I say, it's not mil-spec, so we get nervous when people are going to put this like on a platform with a big weapon system because the vibration and shock may be tough on it. But it's pretty robust.
Sure. So last question, and I believe you referred to this earlier, but maybe it's worth restating. If someone already has the right PXI modules from NI, can they just buy the software from you?
Absolutely.
So you're very flexible in that regard.
Yeah, that's a straightforward thing, and many of these modules are quite popular. You may have to. You may not have the FPGA module. You may have to buy that, because that's required. But if you have a good embedded controller, and in fact, our RTSA software runs on a wide range of NI VSAs. It runs on the VST products. It runs on the 5675. It runs on a lot of different products. Your performance will vary based on the underlying capabilities of that system, but it's a software-defined instrument, and we support a wide range of platforms. What we were showing today was the flagship, but if you have an existing NI configuration, give us a call, drop us an email, and we'll tell you whether we can support it.
Great. Well, that kind of wraps up. We're about out of time. I'm very impressed in terms of the presentation. I think taking the capabilities of the NI equipment and then what you've wrapped around it, particularly on the software side, makes for a really impressive capability that I think will be of interest to a lot of folks. So thank you, Rob.
Thank you.
Also, Michael, for the presentation and the demonstration on modular real-time spectrum analysis. A couple of reminders for everybody before we sign off. Everyone who registered will receive a copy of the presentation. You're going to, within the next, say, 30 minutes, get an email with a link so you can download the slides. Also, we have recorded this, so this will be available to view on demand over the next 6 months. You'll find it in the events section of the Microwave Journal website. Give us about 24 hours to get it posted, and then you'll find it there. And so if you found the presentation interesting and informative, particularly the demonstration, you want to see it again, or you'd like for your colleagues to see it, they'll be able to watch it on demand. So thanks everyone for joining us today, and we hope to have you join us for another webinar in the future.